Because calculus is mostly calculator inactive, it's important for you to be fairly comfortable with each of the parent functions and knowing what they look like and being able to graph them by hand and that sort of thing. So I want to direct your attention to a couple different ones that I think maybe you would be uncomfortable with finding the information without using a calculator. Okay, I know these are really easy to do with the calculator, but I do not want you to use a calculator on any of these. So I think the first couple are definitely pretty comfortable. I do want to direct your attention to this one real quick. That's your horizontal line. So I wrote y equals a just because it could be any number there, but I want you to see that the range we write this way specifically. So if you look at that range value or that y value that you can have, there's only one value there. So we'd say just from a to a, or if the line was y equals 3, it'd be from 3 to 3, or whatever. All right. Then over here, the function is just a simple rational function. Some people call it an inverse function or reciprocal function. So for this one, you know what's interesting is I did not put any names on these. So I would like for you guys to go back and do that as you're going through here, is like write the name for each of them. So you could say like this one's a horizontal line, this is a linear function, quadratic function, cubic function, square root, that sort of thing. You can write their names next to them. And I would typically say that when you're finding these by hand, a really good table of values to find would be from x values of -2 to +2. So if you plug in -2, plug in -1, 0, 1, and 2, that works for most of them. For the reciprocal function, that doesn't work as well. So for this one, I would plug in -2, -1, and -1/2. And then you can't plug in 0 because 1 divided by 0 is not defined. And then I would plug in +1/2, +1, and +2. So that's my hint for this one. I did want to do this one with you guys, y equals ln x, because I think students are uncomfortable with it, and then also because it's very common in calculus. The natural log function, you can write that name, natural log, that function is very common. So here, I'm not going to plug in negative values because you cannot log a negative. I'm not going to plug in 0 because you can't log 0. So I'm going to start off with 1, and actually, maybe I will start off with 0 just because it's a kind of common answer. So I'm going to say 0 here, and then over here I'm going to say undefined. It's good for you to know that ln of 0 is undefined. Okay? Ln of 1 is 0, in case you weren't sure. Ln of 2 is some decimal that's going to be hard for me to get without a calculator. Same with ln of 3. The only other value I'm going to be able to get very easily is ln of e. So I'm going to put an e right here. And you might not remember because we haven't done, or I haven't gotten to the point in the notes yet where we're doing the log section. But if I was to have an exponent with this e, it would be an exponent of 1. And ln's and e's are inverse operations of each other, a log with a base of e and then an exponential term, I guess, with a base of e. Those cancel each other out. So the ln and the e cancel, and this just equals 1. And then with e, it's not necessarily common knowledge, but e is kind of like pi, where it's a special number, and it equals 2.7. So if you know that, we can graph this without using a calculator. So at x equals 0, I have a vertical asymptote. And I have the point 1, 0. And I have the point 2.7 for the x coordinate, and then 1 for the y coordinate. And then I know that log functions are the inverse of exponential functions, which means that it looks like this. Like exponential functions look like that, so with log functions it would make sense that it would look like this. Alright, so that one in particular is especially important. The other thing that I like to discuss with students is the range of a log function, because if you graph it on your calculator, it appears that they stop in your calculator, they actually kind of look like square root functions, but they don't. They keep going, and your calculators just have a hard time with vertical asymptotes, with lines that approach a vertical asymptote. You just can't see them very well. So the range of this is actually from negative infinity to positive infinity. Okay, the next function I wanted to talk to you guys about. So E is going to be similar, actually. Focus. On this one, you could plug in like -1. 1 over E would be kind of hard to graph. You can plug in 0, plug in +1, that'd be 2.7. This one you can use a calculator to find some decimals, but the idea is you want to be able to mostly graph these without a calculator. Okay, the next one I wanted to talk about is how to graph sine and tan, and then you're going to graph cos on your own. And we graph these without a calculator by using our unit circle. So in the packet there's a couple places where I put a unit circle, but one of those places is on page 19. So you have to flip back and forth. So when you're graphing a trig function, typically we're going to focus on the quadrantal angles, like the positive x-axis, positive y-axis, negative x-axis, negative y-axis. And the reason we're going to do that is because they're much easier to graph by hand, those values are, than these crazy numbers right here. So for the sine function, when we graph it, we use the y-coordinate of the unit circle. So we would say for an x value of 0 pi, we have a coordinate of 0, a y-coordinate of 0. For an x value of pi halves, we have a y-coordinate of 1. For an x-coordinate of pi, we have a y-coordinate of 0. For an x-coordinate of 3 pi halves, we have a y-coordinate of -1. And then for an x-coordinate of 2 pi, we have a y-coordinate of 0. And so if you look at that, you can see x-coordinate of 0, y-coordinate of 0. X-coordinate of, this would be pi halves, y-coordinate of +1, x-coordinate of pi, y-coordinate of 0, x-coordinate of 3 pi halves, y-coordinate of -1, x-coordinate of 2 pi, y-coordinate of 0. So that's exactly how we got that. So when you graph the cos graph, you're going to be looking at the unit circle again, but you're going to be paying attention to the x values instead of the y values. So for the cos graph, you're going to say x-coordinate of 0, y-coordinate of 1, x-coordinate of pi halves, y-coordinate of 0, x-coordinate of pi, y-coordinate of -1, x-coordinate of 3 pi halves, y-coordinate of 0, x-coordinate of 2 pi, y-coordinate of 1. So that's how you're going to do the cos graph. The tangent graph is an interesting one because we are going to have to use more values, and the reason is if you use these ones, you'll see tan is y divided by x, so you'd see if I plug in 0 pi, I get 0 divided by 1 is 0. That's easy enough. But then if I plug in pi halves, I get 1 divided by 0 is undefined. So I get a vertical asymptote. And then if I plug in this one, tan of pi would be 0 divided by -1, which is 0 again. But then if I do tan of 3 pi halves, I get -1 over 0, and I get another vertical asymptote. So I can't have 1 point and then an asymptote, and then 1 point and then an asymptote, and even know what to draw. So what we do for tan is we start here and we're actually going to use pi fourths. And the reason we use pi fourths is because if you do tan of pi fourths, you have a y-coordinate divided by an x-coordinate that's exactly the same, which means they divide to equal 1. So for tan, you'd say I plug in 0, I get 0. I plug in pi fourths, I get 1. Then I plug in pi halves and I get an asymptote. And then I plug in 3 pi fourths and I get -1. And then I plug in pi and I get 0. And then I plug in 5 pi fourths and I get +1. And then an asymptote. And so that's why, let me go back, when you look at tan, You can see we've got our 0. Here's the asymptote right here. And so we've got, this is our asymptote. Okay, here's 0 right here. So this is pi halves, 3 pi halves. Here's pi right here. So this is my pi halves, pi fourths. This is me plugging in pi fourths and getting 1. This is my asymptote, plugging in 3 pi fourths, getting -1, getting 0, getting +1, then the asymptote. And that's why you can see right here that the domain is all real numbers as long as x is not a multiple of pi halves. So any multiple of pi halves, and I guess I should clarify that, because it's not every multiple of pi halves. I'll have to look up and see exactly how that's written, because the whole number pi's are okay, it's just the pi halves, 3 pi halves. Actually, here, we're going to fix it right now. You're going to say pi halves plus pi k. That's the correct way to write it. Because then you'd have pi halves and 3 pi halves and 5 pi halves and negative pi halves and negative 3 pi halves. That's how it should be written. Okay. And then on this one, your range, you can see it goes down forever, it goes up forever.